Hi everyone, what's up? Today I want to go over the second fundamental theorem of calculus and how you can, use it to solve some examples, okay? So, before we get into the examples, let's recall what the FTC2 says. So, remember that if we have a function, which I'm just going to call g of x, and we say that g of x is going to be a function that is defined as the integral from a to any input x of the dummy function. We can call it a dummy function because its variables are going to be dummy variables, are going to be placeholder variables, okay? They're not going to, be pretty much relevant. So let's just say this function is going to be, it's actually going to be, I was going to write an actual function, but I'm just going to keep it in as abstract as I can. So this is just going to be f of t dt. And we know that, well, this function, we can actually write it as the antiderivative of f evaluated at x minus a constant, which is going to be the antiderivative of a small f evaluated at a, but I'm not going to do that. And we know that, well, FTC2 says that if we have this function, then g prime of x is going to be equal to f of x, okay? So pretty much whatever function you have in the integrand, the derivative of g is going to be equal to that function inside the integrand, and instead of having an input of t, well, it's going to have an input of x, okay? So this is the second fundamental theorem of calculus, and now let's see how we can use it to solve some examples. So let's say that we have a function. I'm going to call it m of x. No, I'm actually, m of x. Let's just keep the notation consistent, and let's say that this function is going to be, well, it's going to represent the area under a parabola, under one half of a parabola. So let's say it's going to be the integral from 0 to x of t squared dt, okay? So remember, t is going to be a placeholder variable. It's going to be a variable that is just going to describe what function, under what curve we're going to be trying to figure out the area, okay? So t squared is going to be a parabola, and we want to find the area under t squared, okay? That is, that's the role of t. So now, what if we wanted to find m prime? Well, we know m prime of x is going to be equal to the derivative of the derivative with respect to x of this integral, okay? Which is going to be the integral from 0 to x of t squared dt, okay? And based on FTC2, well, we know that we can just grab the function that we have in the integrand, and we can just plug x in wherever we see t, okay? So pretty much this is just going to be equal to x squared, okay? So this means that m prime is going to be equal to the function in the integrand, which in this form is going to be f of t, and instead of f of t, well, we have f of x squared, okay? That's all. So now, what if we wanted to find, let's say, m double prime, okay? Now, if we want to find m double prime, well, we just want to find the derivative of m prime. And even though we're dealing with a different kind of function, which is, functions written as integrals, well, you're going to use the exact same logic as if you were dealing with elementary functions to find the second derivative of m, okay? So you're just going to take the derivative of m prime. What is m prime? Well, we know m prime equals x squared, okay? So we can just say that m double prime of x is going to be equal to the derivative, I'm going to write it like this, using this notation, the derivative with respect to x of x squared, which we just know is going to be 2x, okay? So that's the second derivative of m, okay? So m is just as any other function. The only thing that's different is that, well, we write it as an integral, okay? So let's do another example. So what if we define another function? I'm going to call it w of x, and we say that w of x is going to be the integral from 0 all the way, of course, up to x. And the dummy function that we're going to have, I'm going to say it's going to be sine of t times cosine of t, okay? And dt, okay? Now, what if we want to find the derivative of w? Remember, we're asking the question, what is the derivative of the function? Because in math, when you try to study a function, when you want to understand how a function behaves, it's going to be really helpful to know what the derivative of the function is, okay? And in higher level math, well, we stop using elementary functions as we did before, before calculus, and we start using these type of functions. There are some functions that are called special functions, that are functions that are, you know, written in terms of an integral, okay? And we want to be able to study those integrals, and well, we need to be able to compute their derivatives to, you know, to study these functions as integrals, okay? And that's why FTC2 begs the question of, well, what's the derivative of the function, okay? That's why, you know, in all these examples, I'm asking, well, what if we want to find the derivative of the function, okay? So, you know, I think that was worth mentioning. So what is the derivative of w? Once again, we ask that question because it's information that is relevant to understanding the way w behaves. So if we want to find w prime of x, once again, we're going to take the derivative with respect to x of the integral from 0 to x of sine of t times cosine of t dt, okay? And based on FTC2, well, we know f of t, small f of t, is going to be equal to sine t times cosine t, and we know that w prime, which in this case is going to be g prime, is going to be f, small f, and you know, you can just simply switch the input. So instead of t, well, we're going to have x, which means that double prime is going to be sine of x times cosine of x, okay? So this is what we get for the derivative of double prime. And, you know, just as we did up here with the example of m, if you want to find the second derivative of w, well, you can take the derivative of w prime, okay? And now this is just as you've been, you know, doing in calculus 1. The derivative of w prime is going to be the derivative of this, and you can use the product rule to compute that, okay? I'm not going to do it here because, well, it's kind of outside the FTC2 topic, but yeah, you know how you can, you know, compute this derivative, the second derivative of w, okay? So yeah, that's been the entire video. I hope that you enjoyed it. I think when you get to these types of functions, these types of special functions, that's when you're, you know, getting closer to all the higher level math that you see in textbooks. And, you know, when you go on a physics page, on a physics Wikipedia page, and you see a whole bunch of fancy equations, a lot of them are written as special functions, okay? And maybe you know, a very important function that maybe you've seen is the function that, you know, that can be used to describe the bell curve. The bell curve is just, you know, it's something you see in probability, and that is, you know, that is an example of how you can apply FTC2 and all this stuff, okay? So yeah, you know, this is really cool, and this is, you know, getting closer to way higher level math than you're used to, okay? When you get to Calc 3, this is gonna be important, okay? So yeah, that's been the entire thing. I just wanted to say that, you know, some extra remark, and that's it, okay? So yeah, see you in the following video. Bye.